All right, let's just jump right into it. Welcome to The Explainer. Today, we're unpacking some absolutely fascinating source materials all about our space theory version 1.0. It's this profoundly compelling framework that actually attempts to geometrically integrate relativity and quantum mechanics. Why? To solve literally one of physics' greatest mysteries. We're going to break down some seriously dense, mind-bending geometry today. But hey, don't worry, we're going to take it step by step. So, here's the fundamental, century-old paradox. It's that cognitive itch we're finally going to scratch today. Why on earth does the simple act of looking at a quantum wave suddenly force it to collapse into a defined particle? Seriously, physics has wrestled with this exact question for generations. And the source material we're looking at today offers a radically different, purely geometric answer. Just to ground ourselves in what we're actually up against, think about the classic double-slit setup. You've got those spreading probability waves, right? Before observation, quantum mechanics tells us a particle is a superposition of these waves spread out across space, literally traveling through both slits at the exact same time. But the very second it hits that detector screen, the moment it's observed, bam, the wave function collapses. It just becomes a single distinct point. Well, our space theory proposes a completely new, kind of mind-blowing mechanism for why that collapse actually happens. Okay, so here's our roadmap for the explainer. 1. The mystery of quantum duality. 2. What is our space theory? 3. Space-time from rotation and phase. 4. Solving the double slit geometrically. And finally, 5. Stacked time and space. Let's get into it.
Part 1. The mystery of quantum duality.
This perfectly captures the crazy dual nature of quanta, like photons or electrons. Before we observe it, a quantum entity is basically this continuous spread-out wave. But right in the center, when measured, we perceive it perfectly as a single-point particle. It's not like it's sometimes a wave and sometimes a particle. Its entire nature depends on the sheer act of observation. Now, mainstream physics has a bunch of competing interpretations for this, but our material today, it suggests we've basically been looking at the fabric of reality all wrong.
Part 2. What is our space theory?
The absolutely crucial takeaway here is this definition. In our space, there are 0 standard physical particles, literally none. Instead, the whole thing is pure geometry. Quanta are completely defined by combinations of angular momentum, which the theory calls rotation vectors, and their mathematical phases. And, well, that's it. Rotations and phases, the whole shebang. But that obviously begs the question, how on earth do invisible spinning vectors create the solid physical world we actually see? Part 3. Spacetime from rotation and phase. Let's actually compare how these vectors behave. On one side, you have a photon. It's got a simple one-turn symmetry, meaning it completes a full phase rotation in a standard 360 degrees. But on the other side, an electron is a bit of a different beast. Because it has higher rotational energy, its vectors orbit and precess in this really complex way. It has a half-turn symmetry, meaning it actually needs a full 720 degrees just to complete one single rotation. Now, for an electron to absorb a photon's energy, their rotation axes literally have to align. And because of their differing symmetries, they end up constantly interacting at a very precise 45-degree phase angle. Here's the kicker. In the mathematics of Minkowski space, which is the geometric model of our 4D universe, a 45-degree angle corresponds exactly to the speed of light. This interaction right here, it's the literal genesis of what we perceive as spacetime. So to get from this highly abstract our space into our physical world, there's a really distinct 3-step transformational process. First, these phase circles expand. Second, they get projected down into a format we can actually perceive. And third, that projection forms what we experience as infinite spatial planes. Let's visualize how this actually plays out. Imagine one full rotation of a vector in our space. It translates into this expanding concentric phase circle. Now, to map this to human perception, think of this circle divided right down the middle horizontally. The top half represents the future, and the dashed bottom half represents the past. This expanding geometry, this rhythmic pulsing, is essentially the heartbeat of our space. But, okay, here's the catch, and it's a big one. Because our own bodies, our brains, our measuring tools are all constructed from these exact same rotation vectors, we physically cannot perceive the curves of our space directly. We just can't. Instead, we project those curved phase half-circles outward, flattening them out into straight horizontal spatial lines. It's exactly like taking a globe and projecting it onto a flat 2D map. We live on a curved Earth, right? But we experience the ground locally as totally flat. Well, we're doing the exact same thing with quantum phase geometry. And the crazy part is, the math backs this up perfectly. It maps this projection onto what's known as a Poincare disk and an infinite hyperboloid, which is essentially just a fancy way of translating curved geometry onto flat planes. When these phase circles project onto our perceived straight spacetime, the shifting angles translate mathematically into what we perceive as velocity. So what looks to us like a little particle smoothly zipping through space is in reality just an abstract geometric phase projecting its changing rotation onto our flat perception. Mind-bending, right?
Part 4. Solving the double-slit geometrically.
Now let's put it all together. A quantum, which remember is just a z-axis rotation vector, has its phase expanding chronologically. It's traveling toward the physical barrier and hits those famous double slits. But instead of a physical wave breaking apart, it's the geometric phase that hits the slits. And from those two precise points, two brand new expanding phase circles start to grow and overlap.
Okay, we need a major paradigm shift right here. Normally, this looks like two completely separate waves interfering with each other across a distance. But remember our golden rule. In true R space, spatial distance doesn't exist. There's only rotation and phase. So what look like two separate waves are, in fact, just mathematically overlapping phases of a single unified vortex. It is all one interconnected system.
And this brings us to the absolute climax of the theory. When these expanding phase circles are finally mapped onto our spacetime, they form intersecting light cones which trace out these hyperbola shapes. And here is where it gets wild. If you take the equation of the left hyperbola and just algebraically add it to the equation of the right hyperbola, the result is perfectly a third hyperbola. The geometric phase differences between these merged mathematical pathways dictate exactly where the light is going to hit the screen. That is literally what forms the interference pattern. It's pure, elegant algebra generating physical geometry. Let's just pause for a second to compare this with the standard view. The traditional de Broglie-Bohm pilot wave theory suggests a physical particle is essentially surfing on this sprawling, hidden physical wave that guides it along. R-space theory says, nope, completely drop the physical wave. R-space insists no physical wave is spreading out at all. Instead, only the angular momentum's phase is rotating. The wave is just an illusion. It's totally caused by us misperceiving a rotating vector phase that's been mapped onto flat space.
Part 5. Stacked time and space.
Check out that temporal offset highlighted right there. When you combine those two hyperbolas we just talked about, this bizarre mathematical time gap suddenly appears. Except for dead center, the spread of the phase circles implies that the photon actually arrives at the screen at slightly shifted, different times depending on the path it took. But wait, how can one single particle arrive at different times? Well, the answer provided by this framework is profound. Actually, scratch that. It's pretty much reality-shattering. Time does not flow. Space doesn't just stretch out uniformly. According to our space theory, time and space are geometrically stacked. Think of it like pages in a dense book. We feel like time is flowing like a river, but geometrically, it's just a static, layered stack of phase projections. Because space-time is stacked this way, these hyperbolas aren't just 1D lines, they're actually 2D surfaces extending through Minkowski space. But the internal geometries of these intersecting phases mathematically cancel each other out, so we only ever observe the extreme edges of this layered stack. This means the photon never actually splits to go through two slits. Because time is stacked, it traverses both routes concurrently within the geometry, and we simply witness the wave function collapse at this single final edge of the stack, which is exactly where it hits the screen. And folks, that is the true geometric mechanism behind wave function collapse. It's an incredibly heavy, but honestly beautifully structured concept. So I'll leave you with this final thought to ponder. If the universe isn't made of little hard particles flowing through a river of time, but is instead just an infinite stack of geometric phases projecting an illusion of space, how does that change your perception of right now? Thank you so much for joining me on this explainer. Keep questioning the structure of reality, and I'll catch you next time.